Okay, Irodov. This is kinematics, that section. So I've just completely disregarded everything in before this, right? It it just contains some hints and some tips, notation, whatever. Just let's get to the problems. So 1.1, I just had that as one. So in kinematics, the first question, or whatever this 1 point suggests in that particular section, the first question. So question is, so wait a second, something that now it will work. There's no disturbance. So what's the question? A motorboat going downstream overcame a raft at point A. So you have a motorboat. I don't know, not draw this thing. So point A, like this. This is our boat. Call this thing, whatever. Okay. 60 minutes later, it turned back, and after some time, passed the raft at. Okay, so 60 minutes later, so it would have gone. Oh, and it's a raft. What does a raft mean? Motorboat versus raft. What's the difference? Oh, a raft doesn't have a power source, right? Yeah, it just goes with the water. So it's just flowing downstream with the water, right? So if this is the raft, for example, then it will have moved a little bit and it will be over here or whatever. And okay, so it went to this point in what? So here to here, we required 60 minutes. So 1 hour basically. And then what? Okay, it turned back and after some time passed the raft at a distance L equal to 6 kilometers from the point A. Oh, okay, so maybe the raft is now here somewhere, and then this boat it's on the same point as well. So now this distance is what? L, 6 kilometer. Fine. Find the flow velocity, assuming the QT of the engine to be constant. Oh, okay. Right. Uh, you know what? Okay, this seems kind of because this right. We can just do that. You know what? Take the point of view of the raft. So according to the raft, this guy just goes with V to the right and creates some separation. This separation, whatever it is, in 60 minutes. And yeah, and then it goes back with V, and after some time, now they are at the same place. So separation is now 0. So the time required for that should be 60 minutes, right? Because yeah, the T upon V thing is the same. So this is also 60 minutes. Oh, that just means in 120 minutes it goes L distance. So it's what, 2 kilometer, right? No, 6 kilometer. 6 kilometer per 120 minutes, and that's 2 hours basically. So just 3 kilometer per hour. There we go. That's our answer for the first question. Just 3 kilometer per hour. Next, second. A point traversed half of the distance with velocity v naught. Half the distance. What? Oh, so some part of the distance. Okay, that's fine. So with the velocity v naught, the remaining part of the distance was covered with velocity v1 for half the time. With velocity va, okay, v2. So it's 2. It's not a. v2 for the other half of the time. Oh, okay. I'm understanding what's happening. Find the mean velocity of the point averaged over the whole time of the motion. So just total displacement upon the time. Okay, sorry. So total displacement, let's say that distance that was covered was d, the complete distance that was just d. So d upon the time required. And now how do you find the time? So half of the distance was covered with v naught, right? So just have d upon 2 and that upon v naught. So d upon 2 times v naught. Let's say t naught. So that's the time required for the first part. Then this guy went with v1 and v2. So for half the time, so let's call this thing t1. So t1, or call this t, just call this thing t. So the t is required for the other half distance. So t upon 2 times v1 plus t upon 2 v2. That is our distance t upon 2, sorry. So that just means t is equal to d upon v1 plus v2. Fine. Basically, like d upon 2 upon the average velocity, you could say that. Right. So you got t, you got t naught, add them, boom. So not t over here, it should be t plus t naught. So yeah, it's just gonna be d upon 2 v naught plus d upon v1 plus v2. There we go. This is just, oh, come on. Should I actually calculate? Okay, what? I'm just calculate this thing. So 2 v naught times, I'm thinking that's, yeah, v1 plus v2 upon v1 plus v2 plus 2 v naught, whatever this expression turns out to be. That is the thing. Did they give us any kind of calculation? No. So that's it. Mean velocity of the point. That's just this thing. So yeah, there we go. Next question. Third question. Third question is, a car starts moving rectilinearly, first with acceleration 5 meter per second square. The initial velocity is equal to 0. Okay, that's nice. Then uniformly, and then finally decelerating at the same rate. Wait, what? Uniformly? Oh, so it's the same velocity. Decelerating at the same rate omega comes to a stop. The total time of the, okay, the average velocity. Fine. So you know what? The best way to do this is using a VT graph. So first it goes with acceleration something called it A. A acceleration goes like this. Then some velocity called this V naught, and it goes down, right, with the same negative of that acceleration. So it goes like this, right? And what do we want? So right, then uniformly, and total time of the motion is 25. So this complete thing is just 25. That's what we are saying. Average velocity during that is equal to this. Oh, so you already gave us the velocity. Fine. So this times 25, that's gonna be, call this in T naught because we want generalized expressions, right? So call this in capital T. So capital T times whatever the average velocity is. So average velocity times capital T, that's the total displacement. And yeah, what do we want? How long does the car move uniformly? Right. So we want what this thing is called, this thing small t. So this thing will be capital T minus small t upon 2, and this will be same thing, right? Yes. Then the displacement is just the area. So v naught times t plus v naught. Oh, so it's just these two combined just become one rectangle, and that's why just v naught into t minus t upon 2. But the good thing is that we can write v naught as this time, that times the acceleration. So this will just be a into t minus t upon 2 into t plus capital T minus small t upon 2, and that's going to be a into, I think it's going to be capital T plus small t upon 2 over here, right? So this will be capital T square minus small t square, and that upon 2. That's it. That's the whole thing. So calculate it, of course. So there we go. Wait, what do you want? Find the time. So we just want small t square, right? So you can just go with 2 average t, okay, that upon the acceleration equal to capital T square minus small t square. So small t square is just equal to capital T square minus 2 this. That's our formula. I mean, if you know what, because they told me to generalize everything, I'm just going to put these formulae into our, yeah, answers, and then see what we get, right? So it will be basically two answers. So a two-part answer: first the formula that I will get, and then the value, because the value is of no consequence. The formula is. So the thing is, t square is equal to capital T square minus times this quantity, that times t upon a. Cool. All right. So that's t squared right there. So basically, small t is just equal to square root of that. Nice. Let's calculate this thing. So square root of, what do we have? Our capital T is 25. So 25, take that comma. So 25 minus 2 times of average V is 72. Wait, is this in, it's in seconds and this is in kilometer per hour. Why is that? Okay, fine. So 72 kilometer per hour, 72,000 upon 36. Wait, yeah, 3600 basically seconds, and this would be this many meters. Yes, meters is SI. So it's cancelled. It's 20 meter per second. That's the velocity. So it's going to be 2 into 20 into the time required. But okay, that got out. No, acceleration is just 5 in SI units. So it's square root of 25 into, and just to check, yeah, I mean this thing just gives us this is in units of time. That's why, yeah, it works. 25, then 25 minus this. So 25 minus 8, I think, was 4 times 2 is 8. So 25 minus 8 is just 17. That's weird. Is this how it's supposed to be? Oh, this is not nice. So 5 square root 17. What kind of value actually? I mean, not an integer. It's not nice. Fourth. So the fourth is, yeah, whatever. Okay, a point moves rectilinearly in one direction. Wait, did I take that 4 into account? Oh, wait, maybe I didn't. Maybe I did not. Oh, no. So what was that? It was just this times time required. It was our displacement, right? Oh, I think I didn't take that into account. Oof. So V naught was just t minus t upon 2 times the acceleration, and then the other thing was just t plus t upon 2. So the thing is, it would have been a times t square minus t square, and that upon 4, not this. So this would have been like that. Oh, come on, seriously. So then this will be 4 and not, oof. So 4 over there. Then it's like 5 square root of 25 minus 16. That would be 9. That's going to be 15. As I expected, something went wrong. Okay, cool. Next. So let's go to the fourth one. A point moves rectilinearly in one direction. Figure 1.1 shows the distance traveled by the point as a function of time t using the plot find rectilinearly in one direction. Oh, that's nice. As traveled by the point as a function of time t. The average velocity of the point during the time of the motion. Wait, what? This is S was constant acceleration something? No, nothing. Okay. It's displacement versus time. That's all we are giving us. Fine. The average velocity of the point during the time of the motion. So from 0 all the way till, so over here it's not moving anymore. Its displacement is now, wait. So do we consider it till 20 or not? Or do we, wait, what? Till, what's the motion? Till what t value are we considering the motion? I think by motion they do mean that the velocity is non-zero. That would mean that till 20. So till 20 our displacement goes to 2. So 2 meter upon 20 seconds. So 0.1 meter per second, that's the average velocity. So A, 0.1 meter per second. Okay, talk about B. The maximum velocity. So the maximum slope is, I think this is the maximum slope, right? Yeah. And this slope is something like, why is this not in integers? God, no, we're gonna do that. Oh, so it's going from here to, let's say, till here. So here to here, maybe it's a line, and that, I mean, we can approximate this line. So this would be this thing upon that. So it's 1, 2, 3, 4, 5, I think. So 1, 2, 3, 4, 5, exactly 5 of these. That upon 2. So 5 upon 2, that's 2.5 meter per. Oh, so it's not these two units are not 2 seconds. It would be So it's like 5 upon 2 into what's 1 unit. So 1, 2, 3, 4, 5 of them give 10. That means one of them just gives 2. So 2 into 2 seconds, like that. So 5.4 meter per second. And that would be 1.25 meter per second, I think. That's it. 1.25 meter per second. That is our maximum velocity. Okay, cool. C. The time moment t naught at which the instantaneous velocity is equal to the mean velocity average over the first t naught seconds. What? Oh, okay. The instantaneous velocity is equal to the mean velocity. Oh, averaged over the first t naught seconds. So velocity is just the slope of that thing as we change it, right? The average velocity, of course, the slope of this kind of line. And what we want is the instantaneous velocity should be equal to the mean velocity. First in not seconds, of course. So when would that be? I think somewhere over here, because right here to here you have this slope matching with that slope, right? So maybe somewhere over here, that would be like this. Okay, so 10 plus 1, 2, 3 and a half. So 10 plus 3.2, so 7. So 17, I think at 17 seconds. Okay, 17. I don't know. I'm just judging by the looks of this graph. So yeah, next. 15. Oh, sorry, 5. Why am I saying 15? Fifth question. Fifth is two particles 1 and 2 move with constant velocities v1 and v2. At the initial moment, their radius vectors are equal to r1 and r2. How must these four vectors be interrelated to the particles for the particles to collide? The radius vectors are equal to this and this for the particles to collide. Oh, so with respect to the first particle, the other guy is moving with v2 minus v1, right? And its position vector is just r2 minus r1. So at some value of time, right? At some value of time, these will collide. If that has to happen, then when we collide, when they collide, basically what happens is that r2 minus r, yeah. So this separation becomes 0, and that means the position vector to the first particle of the second, that just becomes 0. So yeah, v2 vector minus v1 vector that times time is equal to r2 vector minus r1 vector. So that is how they will be related. So t is the time for collision, which basically means that yes, their differences are just collinear. This isn't that pretty thing. Okay, sixth. Ship moves along the equator to the east with velocity something. The southeast wind blows at an angle. Okay, so ship is moving to the east. Something like that. Fine, these things are ship. Velocity given. Okay, v naught. Southeast wind, south and east wind blows at an angle 60 degree to the equator. Equator is just okay. So for example, if this was the globe, then right, this meridian, this would be the equator thing. Okay, so 60 degree to the equator, you say. Let's just go with the fact. Okay, let's just assume that this ship, it's on the equator, so it's moving on the equator. Although it's technically not supposed to be like that, but hey, whatever. We'll just say it's moving on the equator. Oh, it is in fact moving along the equator. Right, why did I read that? Oh yeah, Southeast wind blows at an angle something to the equator. So it's because it's in southeast, or say it's something like that, 60 degrees. Velocity v equal to 15 kilometer per hour. Causing v. You don't care what its value is. Find the wind velocity v dash related to the ship. Huh? And the angle between the equator and the wind direction in the reference frame of. Oh, so according to the ship, all these particles of the wind, they are actually going like this because, yeah. So v minus v naught. Huh? Not bad. We can definitely do it. It's just v minus v naught, right? Oh, look, these are nice values. I think so. This thing is 30 degrees. Sorry, this thing is what, 30, and v is 15. So it's half of what v naught is. So this will be better if I draw it like that. So it's half of v naught. That means this angle is supposed to be 90 degrees because cosine of 60 degrees is 1 upon 2. So yeah, there we go. Then what's this wind going to be? Do we have to find the actual vector value of this thing, or just is this in bold? No, it's not. Oh, and also the angle between the equator and the wind direction. I mean, that angle is actually pretty easy. This is our equator, this is our wind direction. This is 60 degrees, this will be 30 degrees. Then this complete thing is just 180 minus that, 150 degrees. So the angle it makes is 150 degrees. And what's the length of it? So this is like v naught. This will be square root 3 upon 2 v naught. So we'll just say that square root 3 upon, it actually should just be v vector minus v naught vector, magnitude of that thing, and in this case it just turns out to be square root 3 upon 2 v naught, because not even going to write this because it's irrelevant to and everything. So 3 upon 2 v naught, which is, what's v naught? You notice this is 15 square root 3, 15 square root 3 kilometer per hour. That's the speed, and it's at an angle of 120 degrees. Sorry, what? 150 degrees. This is 60 degrees. This thing is 30. This thing is 150. Okay, that's it. Next, seventh. Seventh is two swimmers leave point A on one bank of the river to reach point B lying right across on the other bank. Two banks, point A, reach point B lying across the other bank. So maybe something like that. Wait, across, that probably means it's just perpendicular. So B, like this. One of them crosses the river along the straight line AB. Okay, while other swims at right angle to the stream. Oh, so it will get blown like this. Okay, and then walks the distance. Fine. Yeah. He has been carried away by the stream to get to B. Wait, what was velocity? Where did you even mention velocity? So it's here. Of his walking, if both the swimmers reach the destination simultaneously, the stream velocity is given. So that's nice. So v naught. They use the same kind of notation as me. So it's just 2 kilometer per hour. Okay, and the velocity v dash of each swimmer with respect to the water. So that we call this thing v. I'm not going to call this v dash. So that thing is just 2.5. So 2.5 kilometer per hour. Cool. Then the time required for that to that, we can just figure that out. Yes. Okay. So what do we need actually? So they reach the destination simultaneously, you say, huh? Fine. So first of all, the time required should be the same for both of them. Let's just figure out something for the first guy who just swam like this. So this is 2 kilometer per hour. This is like 3 upon 2, huh? Yeah, I'm just gonna use that 3 upon 2 because I think there's a 3, 4, 5 triangle hiding there somewhere. So this is 2 in this direction, there must be 2 in that direction as well, and this thing is just 3. Wait, why is this 3 upon 2? How can that be? Because it's less than this guy, so that makes no sense. What was that? It was 1 point, sorry, 2.5. 5 upon 2. Why am I doing this thing? It should be 5 upon 2. Fine. So this is just 5 upon 2 in that. Then, of course, this thing is just 4 upon 2. So we know this is going to be 3 upon 2. So, yeah, no mention of the distance. Actually, need to be tried. For this in D. So D upon, well, 3 upon 2. That, okay, whatever. No, just do it. D upon 3 upon 2. That is the time required for this guy to go there. Fine. And the other guy, the time required for it to cross it, that will just be D upon, so it just goes like this, right? So 5 upon 2, and then plus the fact is it also goes like this. So it's 5 upon 2 in here, and then 2 in that direction. Also in the same amount of time, 2 times of that. So 2D, sorry, why am I this? Right, 2 because this thing is 2, so it will have flown down that much. So 2D upon 5 upon 2, that will be this length exactly. And well, what after that? Once you got what this length is, oh yeah, so the time required for that. So this is that length, and then that length divided by the speed. So this, all of this upon u, that's the time required. All of these must be equal, and there we go. So 2 upon 3 is equal to 2 upon 5 plus 4d upon 5u. Sorry, 4 upon 5u, not p over there. So u will be in kilometer per hour, and d was in whatever unit it was. So yeah, 1 upon 3 minus 1 upon 5 is equal to 2 upon 5u. So right, this is 5 minus 3, 2. 2 upon 15 is equal to 2 upon 5u. So you can say 1 upon 3 is equal to 1 upon u. So u is equal to 3 km per hour. So u is equal to 3 km per hour. Next. 8. So 8 is two boats A and B move away from a buoy. So a buoy is just something that is floating on water. It's standing still most likely. At the middle, oh, so it's a river. No, if it's a river, it's moving as well. Wait, it's anchored, then it's not moving. Fine. At the middle of a river, along the mutually perpendicular straight lines. Huh? The boat A along the river and boat B across the river. Oh, okay. Starting to understand what's happening. So B is moving like this, A is moving like this, and there's this boy, right? Having moved off an equal distance from the boy, okay, equal distance from the boy. Wait, so they both start at the boy, I think. Away from a boy, fine. So yes, they both start at the boy. Moved off equal distances from the boy. If the boats returned, find the ratio of the times of motion of boats. Wait, what do you mean? Oh, so when they move off an equal distance, they just, it doesn't make sense. If this guy's velocity is different in this velocity, then they will never move the equal distance, right? Oh, okay. I mean, of course, that's going to happen, that they will have different distances at at the same time. So just set an arbitrary distance that they have to go. That would do it. Find the ratio of the times of motion of boats TA upon TB. If the velocity of each boat with the water is this thing, times So just set the stream velocity as 1, then this will really be nice. So just 1.2 in that direction, 1.2 that direction. Cool. Or maybe set it as 5, so this will be 6. The good thing is that, oh, okay, so with respect to the water is this thing. Fine, 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 fine. It's doable. It's doable. It's not that complicated. We can definitely do it. Yes. 1.2, you say. So for this guy to move along this line, what should happen is this thing is 1.2. This thing is 1. This thing is 1, right? So what will this be? The square root of 1.2 square minus 1, right? So square root of 0.44. Yeah, square root of 0.44. No idea what that is. So 0.2 times square root of 11, I think. Yeah. 0.2 square root of 11, that's this guy's velocity, yeah, along that direction. So time required for that. So t1, that will be whatever distance we have. I also said that distance will be 1, in fact. So it's just 1 upon 0.2 times. So no, 2 times of that, right? Because, yeah, square root of 11, like this. Okay, and t2, that will be, so first it will have to go downstream, and that's why 1 upon downstream velocity is just discuss that. It's going to be, so that was 1, right? So 2.2, and then plus upstream velocity, just 1 upon 0.2. There we go. It's t2 for you. And now we can take the difference, the ratio of this thing. Just want ta upon tb, whatever. So ta is the one along the river. That means just the one with t2, right? So this thing upon that thing, no big deal. So you can just get rid of these points. It's 1 upon 22 plus 1 upon 2 upon, so basically just 1 upon square root of 11, right? You can write this thing as 22 and then 11. So 12 upon 22, that is just 6 upon 11. So 6 upon 11 times square root of 11, that will be 6 upon square root of 11. Cool. That's the ratio. Good thing it's just a ratio for the units. Next, ninth. Ninth is a boat. Where is it? A boat moves relative to water with velocity which is 2 times less than river flow velocity. Relative to water with velocity 2 times, okay, less than the river flow velocity. At what angle to the stream direction must the boat move to minimize drafting? Sorry, drifting. So yeah, you can just get rid of the drift, right? Because it's 2 times. Wait, what? It's 2 times less than the river. Oh, so this is very different now. Okay, so the river is flowing like this, whatever it's doing, and so your drift should be the least. Huh. Oh yeah, this is going to be very, very hard to do. So call this thing, we'll just say this thing is 2, then this thing will be 1, pointing somewhere over there. Say this angle is theta, right? That's the angle. What do we want actually? Angle to the stream direction. So then we'll say, okay, you know what? This angle is theta. Yeah. Okay, cool. Fine. So what's the horizontal velocity? Is just sine theta, right? So sine theta, and yeah, so like d upon sine theta, v sine theta, and whatever. Just let that be 1. We'll just see what function we want to minimize. So 1 upon sine theta, that would be the time required. And then what's the drift? Drift produced will be this times 2 plus cosine theta. Exactly. You want to minimize this thing. Fine. Seriously. Why do you want to minimize this thing? How would you minimize this thing? Just take a derivative, of course. So 2 cosec theta plus cot theta, right? We want to minimize this, so just take that guy's derivative. then it's just -2. Well, it's going to be negative anyway, so cancel that. So 2 cosec. One thing could happen is that cosec theta could be 0, which is basically impossible. Another thing would be cosec theta, and then so no, well here you would just have 2 cot theta, because cosec theta derivative of that is cosec theta cot theta, but negative of that, of course. And then plus cosec theta should be equal to 0. So your cosec theta should be -2 cot theta. So basically 1 upon sine theta is equal to -2 cosine theta upon sine theta. Isn't that right? So cosine theta should just be equal to -1 upon 2. That is when this thing. So there's only one extremum value that you got, probably because that minimizes the drift, right? Yeah. Whatever. So cosine theta equal to -1 upon 2, which looks intuitive, yes. Which is basically 120 degrees. Hey, is that? Oh, okay. So this is only for this particular case when it's 2:1. What if this is not 2:1 or is something else? So what if this n:1? Then you would have to minimize n cosec theta and all that stuff. So it would be like that. So yeah, it would be -n over here, and then yeah, cosine inverse of -1 upon n, that we think, which is basically just pi minus cosine inverse of 1 upon n, right? So pi minus cosine inverse of 1 upon n. Here n is equal to, wait, did they actually give some notation for that? Where did it go? 9, right? Yes, n. They also used n. Nice, that's intuitive. So here n is equal to 2. Okay, why even do that? Just write it that it's equal to 2 pi upon 3. There we go. Next question. 10th. Nice formula. Fine. Two bodies were thrown simultaneously from the same point, one straight up and the other at an angle something to the horizontal. The initial velocity of each body is equal to, okay, neglecting air drag, find distance between the bodies this much time later. One straight up, other at an angle of something to the horizontal. Okay. Initial velocity of each body is just 25. So the first guy is just going, let's talk about the second guy first. The second guy is going like 25 over here and it's at angle 60 degrees. Find the distance between the bodies at t equal to this time. Oh, okay. Fine. So you can just figure out what the equations of motion will be. So for this guy, displacement, so as a vector, of course. The first guy that's just thrown up. For that guy, there's no x coordinate displacement, just y coordinate displacement of whatever u we have, right? So u minus, yeah, let's just go with theta, whatever. Hey, actually, theta equal to 60 degrees and v naught. So we'll go with v naught, not u. So with v naught minus g upon 2. Sorry, it's the displacement that we're talking about, right? Or what are we actually finding? Distance between the particles. Yeah, just the coordinates basically. Just find the coordinates of the particles. So v naught t minus g upon 2t squared. That is our coordinate for this guy. And for this guy, it will be v naught cosine theta t, and then v naught sine theta t minus g upon t square. And at some particular t, what's the distance between these two? That's what we're looking for. That will be so square root of, but take that t out, because of course, oh, you could just took the relative velocities, right? Yes, you just took the relative velocities. This is so stupid. Why are we doing it? There's no need for us to do it, right? Just figure out the relative velocities. The first guy has the relative, so the first guy has velocity 0 comma v naught, other guy has velocity v naught cosine theta comma v naught sine theta, right? So the relative velocity of the second is to first, that is just v naught cosine theta comma v naught sine theta minus 1. Cool. And And now we just need to figure out what the magnitude of this thing is, right? Yeah, exactly. So that we can figure out what distance should be. No, sorry. That is, in fact, yes, that is correct because it's just moving directly linearly, and they were simultaneously, they were at the same position when we threw them, right? Yeah, simultaneously from the same point. Nice. Just fine. So basically, it's just one of them is just moving away from the other. That's it. What's the magnitude of this? So square root, I think that would be not common. So v naught square root of cosine squared plus 1 minus 2 sine plus sine squared, whatever. So v naught square root of 2 minus of 2 sine. Yeah, whatever. And to the horizontal, of course. That's why this thing. Fine. So this is just sine. And hey, we know something that we can do. So we can just write this thing as v naught square root of 2 into, so 1 minus sine. Okay, no, just leave it like that. Don't simplify it any further. But I really did want to simplify it. Just do it. Just do it. If I want to, I will. Minus cosine of theta minus, sorry, cosine of pi by 2 minus theta, right? And in that case, we can do this. It's going to be 2 sine squared of pi upon 4 minus theta upon 2. There we go. So 2 v naught sine of pi upon 4 minus theta upon 2. So theta, it goes from 0 to pi upon 2. That means it is less than pi upon theta upon 2 is pi upon 4. So this thing, it is just, its maximum value is pi upon 4. So it's, yeah, it will work. No need for mod of that or anything. It's good as it is. So it's going to be 2 v naught sine of pi by 4 minus theta upon 2, huh? That's it. That is our, that's our magnitude of the velocity. What do you actually need to find? That times t, of course. Hey, not a big deal. And now let's calculate it. So 2 times of, okay, 2 times of, well, v naught is what? What's v naught? Where did it go? 25 meter per second in SI, so that's nice. Sine of, what's time? What's the time required? Time required is 1.7. Okay, and then this quantity. So theta is 60 degrees, so it's like 45 degree minus 30 degrees is sine 15 degree. Wait, what? Are you serious? You are saying it's sine 15 degrees right there. Oh, come on, I should have done that. Just square root of 2 into 1 minus sine. That was the best thing one could even do. So yeah, square root of 2 into 1 minus square root of 3 upon 2. That would have been the best thing to do. That's it. That's where we stop. No, go further. 4 minus 2 square root 3 upon 2 basically. So this will be square root 3 minus 1 upon square root 2. There we go. Which is square root of 6 minus square root 2 upon 2, right? You can just put that value in it. So, or you could put this value. I don't care. Square root 6 minus square root 2 upon 2. That's it. This is our value. So, that 2 got cancelled anyway. So, it's just 25 into 1.7 into this thing. Why? Okay, so 25 times this thing. Let's do it. 5 times this is like 5, 35, 8.5. That times 5, it is 400 and so 2.5. So 42.5 times square root of 6 minus square root of 2, whatever this value is. So in this case, unfortunately, we got something like sine 15 degrees or whatever. 11th. Two particles move in uniform uniform gravitational field with an acceleration g. Okay, at the initial moment, the particles were located at one point and moved with velocities this and this horizontally in opposite directions. Oh, so opposite directions, huh? So you are not saying they are on ground or anything. Okay, fine. So somewhere in the air. Yes, and then moving like this and this. Find the distance between the particles at the moment when their velocity vectors become mutually perpendicular. Oh, okay. So distance between that. I mean, okay, it's just the relative velocity is seven times whatever the time required is when that happens. So you want their velocity to become mutually perpendicular. Okay. Wait, but are these velocities in okay horizontal? That's awesome. The first guy maybe it has velocity of negative. So g upon two, you don't know what g is, huh? Wait, what? Acceleration g. I think we just have to use the fact that g is approximately 10, or do we not use it? Because this has numeric values, and to get a nice answer, we have to do it. It's gonna do it. Let's say g is equal to 10, whatever. So g upon 2, that's just 5. So negative 3 and then 5t. Sorry, negative 5t. That's this guy's velocity. Another guy just has 4 comma negative 5t. And what we want is that their dot product should be 0. So negative 12 is equal to so 12 is equal to 5t squared. So 25t squared. That's like 2 upon 5 square root 3. Huh? And that times the relative velocity, which is just 7. So 7 times that is going to be the distance between them. There we go. It's just 14 upon 5 square root 3. Next. Huh, that's weird. I mean, you could just write it in terms of V1 and V2. Oh yeah, we should probably be doing that because that will be the better thing to do. Okay, so in V1 and V2, this will be that. So this will just be V1, V2 is equal to uh, GT. Oh, why did I choose 5 only? It should be 10T. This is just not good. Sorry. All of this is wrong. So V1, V2 should be equal to GT squared. That would be the thing. And that just means T is equal to square root of V1, V2 upon G. That's when this happens. And then this times the relative velocity, which is just V1 plus V2. So our answer would just be V1 plus V2 times square root of V1, V2 and that thing upon G. Now for uh, this case V1 is 3, V2 is 4. So this is just 3 plus 4, 7. 7 times square root of 3 times 4. So that's 12. So 2 square root 3. 2 square root 3. And that upon G, which is 10. So something like that. 7 square root 3 upon 5. I'll just throw it like that. I won't approximate it whatsoever. Okay. 12. 3 points are located at the vertices of an equilateral triangle whose side equals A. They all start moving simultaneously with velocity v constant in modulus. Oh, hey, I think we have done this kind of thing, right? Yeah. Okay, so how soon will the point converge? Right, that's one thing. And then they could also ask you what's the acceleration that each of them actually has. And yeah, so answer to that would just be v squared upon r cosine of pi upon n, where in this case n is 3. So just remember that. Not really useful for this particular problem, but I did a whole video on this thing because it's a really nice thing to do. And just check that out. Anyway, so this is actually very classic because all you do is just figure out what's the component of the relative velocity along the side, because that gives us the rate of decrease of the separation, and then just figure out when that separation becomes 0. Yes. So this guy, because it's an equilateral triangle, just have this side. The other side, it's like this. At 60 degrees, like that. Now this thing is v. This thing is also v. So what's the relative velocity along this? That will be, this thing is cosine, right? So we want along. It's v upon 2 in that. So just v plus v upon 2, that is 3v upon 2 is how fast this is decreasing. And that times whatever time required, that's going to be our distance and side length a. So there we go. T is just 2a upon 3v probably. That's how fast they will basically converge. Wait, where did it go? Oh yeah, 12th. So that's it. 2a upon, hey, you gave us any values? No, you didn't. So just gonna put that in there. 2a upon 3b. Next question. 13th. Point A moves uniformly with velocity v so that the vector v is continuously aimed at point B, which in turn moves rectilinearly and uniformly with v with velocity u is less than. Hey, I think I've seen this question somewhere in the past. Like maybe one of my tutors made me do this. I think, yeah. So let's go to the next slide, page, whatever. So what are they saying? They are saying that that one of them is just moving uh, rectilinearly like this thing. So maybe it's moving like this, whatever. Initial moment v is perpendicular to u and points are separated by a distance. Oh, sorry, by a distance L. Uh, yeah. So if the thing is that it's right, I mean the whole thing is that this guide has this u aimed towards that other guy, right? And that guy is moving with v, and thing is v and u are perpendicular. That means it's moving like this. So this is perpendicular to this velocity, right? That's why I'm using this thing. So I'll just say, okay, you know what? Instead of doing this, let's just go in this kind of framework. So over here you have this particle. It's initially it was at what distance? Initially it was at L. This guy is the one aimed at B that moves in what? Oh, so B moves with velocity u, and this is moving with velocity v, right? We need to figure out what, how soon will the points converge. Oh, fine. Maybe write some differential equations or something like that. I mean, we could actually. So this guy's coordinates is just given by ut comma 0, right? This guy's coordinates we don't know. Let's say it's at x comma y right now. Then this guy's velocity is going like this, right? So what's this unit vector going to be? Because that's what we need to figure out, the velocity as a vector. So that vector is along. Let's go from here to here. So it's going to be ut minus x and then negative y, and then divide by the magnitude. So 1 upon square root of ut minus x squared plus y squared, and that times this thing. Right. So that is our velocity, and that's just equal to the yeah. So what was I saying? Sorry. Right. This is equal to dx to this thing, dx upon dt, comma dy upon dt. Right. Exactly. Oof. All right. So I mean, okay, this is bad because oh no, it depends on this quantity as well as that quantity. That is just not good. First thing it will do is we'll say ut minus x is x dash, or yeah, no, say that's equal to negative of something. Just give it z used for the other coordinate, but still let's just say it's equal to z for solving this differential equation. So basically what we are saying is that negative z comma y upon square root of z squared plus y squared, and that would basically be equal to this thing, right? So dx upon dt, it's, if you differentiate this thing, that is just u minus dx upon dt is equal to negative dz upon dt. So dx upon dt is just u plus dz upon dt, and then we got dy upon dt. And now we need to somehow solve this differential equation to get when your particle come together, whenever they come together, your y becomes 0, right? And your x becomes ut. So basically we need to figure out when does z and y become 0. Yes. But without actually solving this, how would you figure that out? That's kind of a hard thing actually. Oh, so you know what dy upon dt is? Oh, so you can just kind of do that, huh? Hey, why not do it like that? So don't do all of this. Instead, just use the fact that okay, dy upon dt is just negative y upon all that stuff, and then dx upon dt is that. So dy upon dx, that would just be y upon ut minus x. Cool. I mean, of course, it changes with time and everything, but still, it's very nice, right? It's better than that at least. Well, it's getting complicated. Now what? It's it has this time involved in it, and that is not nice. I need to get rid of this time somehow. How would I do it? Oh, this time's v. Sorry. It should be v over there, but does it even matter? No, it doesn't. So it's this thing. So dy upon dx is equal to this thing, but it's not in two equations. It has three variables. Sorry, that's problematic. Let me just go with dt. You just want the time required, right? Sure. Man, how bad is this? So dy upon dx, that's equal to this. We know that as it goes like this, it's gonna form this kind of curve. I really wish to figure out this curve because last time I solved this, which was very much before this time, the way we actually did it was kind of cheating. We didn't figure out what this curve was. We solved no differential equation. This was some kind of something that just let us find a time. That was not nice. Because I always wondered how would you actually solve this, not just like that, but actually solve it. The chase problem. Nice equation, but then it's got this t in there, and that just ruins everything. On dy, it's so like dy upon the velocity in the y direction. I'm just gonna integrate that thing, and that will just give us what the time required should be. And what's the velocity in the y direction? Well, it's just equal to negative y upon all that stuff. Oh, wait. So just write down some equations first of all. The time required is equal to integration of dy upon the velocity in that direction. It's going to be negative y upon square root of ut minus x squared. So call all of this as r right now. I'm just call this as r. So it depends on distance, like yeah, like that, huh? Okay, cool. So from y is equal to basically L to now 0. So this will just be integration from 0 to L of, so you have that negative, you can just write this thing as R and then 1 upon V dy. Cool, no problem till now. And same thing we can write for x coordinates as well, right? So t is equal to, what was this once again? Yeah, it's dx upon the velocity. So it's going to be 1 upon V 0 to L R. Oh, it's not R actually, unfortunately. It's got that y. Oh, it should not be this. It should be negative V upon R times y. So it should be dy upon pi. And now it's going to be the same thing, except it's just dx upon ut minus x. Not nice. Not nice. So it's from whatever time required you have. Yes. So we don't know where these actually come together, right? Huh. Wait, we do in fact know. So it's from 0 to capital okay, t times u, right? So u times capital T that is when these will meet. Yes. Okay, that is nice and all. How is this even helpful? It's not actually doing anything. Oh, this is a nice. I mean, we just know that wherever it has been set to y should be 0. Okay, this kind of problem. Is there a proper solution for this? You know what I'm thinking? Because it's an inertial, okay, doesn't matter what kind of frame this is. Uh, right, we got the differential equation, everything cool. What else we could do? We could just, write everything according to this guy in polar coordinates. Yeah, that would be, oh sorry, why did this happen? That would be another nice thing to do, right? Yeah. Oh hey, that would really be nice actually. So it's always this and this, like that, huh? So there's always this ut in that direction, cool, and it's something in that direction. So you can just write, okay, you know what? Yeah, just do it. Just write it like that. Maybe in that way we can actually get a more intuitive explanation for whatever is happening. So this is our point B that's being chased, I think, and this is our point A. It's moving with B in this direction, and it is ut in that direction. What is, let's call this angle that it makes with this as theta, right? Initially your theta will be 90 degree, and finally maybe your theta is 180 degrees or something, and your r value, so this complete thing we just call this thing as r. So you just have v minus this. What will this angle be? Look, this angle is theta, right? The one at, yeah, this is just going to be pi minus theta. So okay, calm down. Cosine of pi minus theta, that is negative cosine of theta. Exactly. So v minus ut and then negative cosine of theta. So v plus ut cosine theta. That is dr upon dt. And what's d theta upon dt? So d theta upon dt is still just really bad, but we'll see what happens. And d theta upon dt, that is this upon that, right? So that will be sine of pi minus theta, which is sine theta basically. So ut sine theta, right, and that upon r. So that's our equation, cool. And now we somehow want to figure out. It's not helping at all. Now what? So you got this, good. Now what do we do with it? It's not helping. Come on, think of something. And we just want the time required for r to become 0. We don't have r as a function of time. How am I supposed to solve this? We could just say r is equal to v times t. So let's go from r going, so since we are integrating, we could just say definite integration. So r goes from this to that, right? So dr, it's just negative of what was this then? Negative L, right? Oh no, it should be negative over there because that explains everything. So this is supposed to be negative, that's supposed to be positive. Fine. So L is equal to, so V times whatever time required, and then plus integration of ut times cosine. Oh, it's not supposed to be ut. Why is it supposed? It's not supposed to be ut like that. This is just u. Sorry, I mean the coordinate is that, but this is u, so it's not supposed to be ut anywhere. It is just v. Sorry, u, just u, not ut. So this should be u sine theta upon r. Maybe this is more doable. Yeah, this looks much more doable. Okay, so this is plus u integration of cosine theta dt, and it goes from 0 to whatever time required is, and then you can integrate this thing as well. This is going to help us? I don't think so. Wait, did I see that? No, okay, there's that r over there. Mm-hmm. Fine. U cosine theta dt. What is that exactly? Okay, isn't u cosine theta just supposed to be u like that, right? So u is this. Theta right there. Okay, this is getting really, really bad. Wait, oh, now I remember what we used to do. So what we actually used to do was figure out what v cosine. So we know that the x component of this velocity, that's just going to be v cosine theta, right? Where this is our angle. So this angle theta, and then got v right there. So this whole angle is just theta. Yeah, like v cosine, negative v cosine theta. How does theta change? It's got to change with that, right? Yeah, whatever. So pi minus theta. So v times that thing, that would just be negative v cosine theta. So negative v cosine theta dt, that from 0 to whatever time required, that would be the x displacement by this particle, and that would just be equal to u times tau. Why did I use this fact? This was obvious. Okay, this is much nicer than anything. Why did I use this, and why didn't this fact show in here? Huh, that's weird. So d theta upon sine theta, that is equal to, okay, this is getting really bad. Just have this equation and this equation, that's it. Isolate cosine theta somehow. D theta upon dt. I mean, is this actually solvable? Okay, you know, we know how to get it. From here, we can just say that u cosine theta dt, it should be just, we just do it like that. So you get the idea, right? So is, I mean, okay, so just put negative because cosine theta is always just negative. So just have this, and from here you can say, okay, integration of 0 to t of cosine theta dt, that would probably just be equal to negative u times t upon v. So just put that in there. So you just get L is equal to v times t minus u square t upon v. Yes, it's doable, I understand that, but not what I want to do. Wait, okay, fine. VL upon v square minus u square is equal to time. We get that, right? We get that, but we don't want this. We want something better than this. We want to solve these two equations and get a formula for r and theta in terms of time. Why won't it allow us? What's happening? Why is it in two different? It's really bad. Oh, so the thing is, wait. Did I see this correctly? There's no time dependent terms anymore. Oh, wow. Oh, in fact, in the previous thing as well, there should not have any time dependent terms. The whole thing that came out was because I mistook u for ut, and that's why everything was going wrong. So now, because there's no time dependent terms, just divide these. Oh, this is awesome. So just have negative, let's say, dr upon d theta. That will just be this thing. So v plus u cosine theta upon u sine theta, and then that times r, of course. So there we go. Negative dr upon r is equal to v plus u cosine theta upon u sine theta, that times d theta. So yeah, you want to integrate that. It will be very hard, but Must be something that we can do, right? Exactly. There must be something that we can do all of the time. Yes. So it's doable. You can find r in terms of theta, and then once you have that, just plug that in this thing, and then you will have theta in terms of time. And once that happens, you have everything basically. So yeah, I'm gonna do it after this video. So yeah, let's see you guys in the next video in that case. This is a very nice problem. I mean, I even gave it 2 or 3 tries in the past. I don't remember when, but maybe 2 years has passed. Right. This is a very nice problem. So I will do this in detail now. So I'll see you guys in the next video.